This presentation is about how to move towards an orchestrated 5G open core for Telco NFV. It's a shared presentation where we invited our colleague from Facebook, Amar Padmanabhan, and Gianpietro and myself from Whitestock are going to be talking about Whitestock and WhiteNAV, that is our distribution of OSM. So the general agenda for the presentation is in the next slide. So Amar is going to be talking about Magma. Magma is a Facebook project for creating a virtualized evolved packet core that everybody that was in the Hackfest this week got familiar with. And we are actually working with Facebook in some deployments in production. So Amar is going to be talking about Magma, and after that, we're going to be closing with some notes about Whitestock and our distribution of OSM. So Amar, whenever you're ready, please go ahead, and thanks for joining this presentation.
Thanks everybody. Quickly introduce myself. I'm Amar Padmanabhan. I'm the lead engineer on the Magma program. One of the things that I want to make sure everyone leaves the room with is Magma is a fully open source project that's licensed under BSD, and we welcome contributions as well as multiple users adopting the platform. And as part of that, we're actively engaged in moving Magma out of a Facebook incubated project into a more public location, along with the Linux Foundation, OpenStack Foundation, and TIP. And so if as an organization there is some interest in joining this collaboration effort of a converged core that supports multiple access technologies, feel free to reach out to me offline, and we can figure out next steps. Okay, so a couple of things that we wanted to anchor on is Magma actually looks a little different than what we call regular EPCs or virtualized EPCs, depending on which form factor you're looking at. And a lot of that is informed by our experience running a very large data center with a lot of dynamicism in it. And so there are two key tenets that we took away from our data center that we wanted to bring into access technologies. And so the first one I'm going to talk about is the decoupling of the edge versus fabric. Yeah, so hopefully this is a familiar concept for a lot of folks. But so back in the day, even like 5-6 years ago, when you looked at the Facebook data center, we had a lot of choke point devices that were load balancers, firewalls, and various network functions that were in network. And as Facebook data started growing, and the need for us to adapt both our infrastructure, depending on, let's say on Sunday everyone's watching videos, and so we don't want to run like our Hadoop workloads, and on like Tuesday no one's watching videos, and we have an ability to run Hadoop workloads. So there was a lot of dynamicism in the network, and choke point devices were fundamentally not suited towards this because it forced a network topology where the network services were not adaptable to the actual needs of the what the workloads required. And so a lot of what we've heard in this over the last 3 days is around the importance of orchestration in solving a lot of these problems. But for us to be able to orchestrate a network efficiently, we need to actually design the network in such a way that is amenable to sort of orchestration. So if you look at the data center now, and this slide is from a couple years ago, and it's a fairly well understood concept now with a spline leaf architecture. But the idea is that we removed all network services that existed within the network and moved all of the exact same functionality that we had around load balancing, DDoS production, firewalling, all of that onto x86 servers that were notionally located on the edge. What this did is, it sort of decoupled the network into two completely disjoint spheres. One was the actual fabric that was just responsible for moving packets faster. And then the other one was an x86 based sort of platform where we're sort of innovating by adding newer and newer network services. A lot of the work that we're doing on the Linux kernel side around eBPF and all those are just advances in the way that we're building a Linux platform that can handle more sophisticated sort of network functions. So I think the key takeaway that I want to try and align on here is that there were a few things that we took away from our data center experience. The first one is that if you distribute the policy enforcement point, you have the ability to place the policy enforcement point wherever it is needed, right? Like you don't have to pull your traffic back into California if you could egress that traffic out in Singapore. So the topology that the network presented was what we decided to use for policy enforcement points. The second one is by distributing the policy enforcement point, the aggregate throughput that you need to handle on each node is actually not that high. So this makes it very easy for us to move these things using even more modern technologies like SRIOV and IO pass-through, eBPF, and all of these things to actually move policy enforcement point to purely software. Right, so this allows us for like rapid iteration, and we don't know what the network workload of next year is going to be, but we know that we have a platform that allows us to innovate for that. The third thing is that by keeping the core network simple, we start driving a lot of the cost efficiency. So if we move an access network into like an edge and purely backhaul and IP fabric, then you have the ability to push down the costs of like running a large network infrastructure because you're going to manage it just like how you're managing your existing fiber or IP assets. And then the last one, and I think this is the key takeaway, is that once you've taken out this one giant central box and you made it about distributed nodes, the problem becomes about orchestration, right? And so having a good orchestration layer is very critical because now suddenly you have like a bunch of nodes that are like independently acting. And so leveraging purpose-built systems for FCAPs and plugging into network orchestration and a lot of the interesting stuff that we heard earlier today is sort of the export the brain out of the fabric and the edge into a more central orchestration node, and design your device layer in such a way that it is very introspectable, right? So stream events, like there was a comment on gRPC, those are all things that are fairly robust and usable, and so keep the device as introspectable as possible so that the orchestration layer can do all of the thinking for the device. So roughly, if you take a fixed wireless access sort of a use case, what this means is that we can run these distributed nodes, which we are calling as access gateways, at the edge, and you can run this in a 2-core like Atom box, or you can stack these like pizza boxes in a more central location at your edge data center, and then you get aggregate benefits of throughput. But at the end of the day, the network topology that is driven by your use case defines where your policy enforcement points are. We are just building Lego blocks and tying back into a higher level orchestrator. The second aspect around is agility, right? So one of the core tenets, and one thing that we actually value a lot, even in our data center, and presumably with Google and Amazon as well, is our ability to roll out upgrades as fast as possible. So for example, we upgrade our fabric every Monday, right? So this is a significant amount of infrastructure that gets upgraded every Monday, and the reason we're able to do that is we design for upgrades. So fundamentally, for software delivery to be successful, we need to ensure that nodes are not too big to fail. There is a way for us to contain fault isolation. So like for example, in this picture, this is a fairly illustrative diagram, but the P gateway and the S gateway are like choke point devices. Now, if I take out a P gateway due to a failing upgrade, my chance of affecting a significant amount of the traffic is actually pretty high. And so, it's sort of a too big to fail model. And this was sort of the issue that we had even in our data center 4 or 5 years ago before we took apart the nodes into more distributed elements. So what we're sort of envisioning here is that, we break apart this, what was like notionally an EPC, into more deployable nodes that are like of smaller, radius. And so each distributed node in currently, at least in the Magma architecture, can support up to 12 eNode gigs, so about an aggregate throughput of 9 gigs. And so you're looking at, if for whatever reason an upgrade failed, you have the ability to either roll back or contain the fault to a particular, like say, site or region, and so you don't have like a large scale outage. The second thing that this allows, and this is natively supported in the element manager or the Magma orchestrator, is the ability to do like rolling upgrades. So this allows you to structure your infrastructure into like tiers. Like I have a test tier, I have a pre-production tier and a production tier. And every time a build goes out, it automatically upgrades only the test tier, verifies that the metrics are still where it needs to be after the upgrade, then a pre-production tier, and then a production tier. So we call this canarying. And so this allows to actually both reduce the risk of rolling out an upgrade as well as gradually upgrading it. So upgrade is a first class like sort of principle into the network. So what does this mean when you're thinking about 3GPP is that if you can introduce a level of dynamicism in the network, then you need to only design and implement your network based on the functionality that you need today. You don't need to make big bets on what is it that your network's going to look like 2 years from now, because hey, it's all software. We know how to deliver these upgrades, and so we are able to orchestrate all of these things through a higher level orchestrator to contain the faults, and we don't need to make a large bet. And so in the Valley, this is called the hacker ethos, where iterative development is where you reveal like future like benefits. And so building a platform that fundamentally allows for that is actually, at least in our opinion, pretty critical. Yeah, so what are the principles of the software upgrade? So there's a small upgrade domain. Each node is independently upgradable. And we also have a notion of a hitless upgrade. So when you upgrade a node, the existing user sessions are preserved because they get cached in the kernel. So there is zero downtime for existing user sessions. And then gradual rollout, as I described, is baked into the platform. The second one is that the control plane upgrade is independent from the data plane. And so the element manager, as well as some of the control functions that are implemented in the element manager, can be upgraded independent of the gateways. And the only side effect one may have is during the upgrade of the Magma orchestrator, you may, if you take out the entire orchestrator, you may have some signaling downtime, but for the most part, any user that is actively on the network is not going to be affected, because we cache auth vectors and everything at the access gateway. So quick solution overview. So out of the box, we're focused primarily on 2 use cases today, and these are the ones that are in production. Fixed wireless access, we're adding support for 5G as part of the open core effort. NSA is around the corner with the existing code base. Carrier Wi-Fi is our spin on mobile data offload, where we dominate all of the radius and GRE tunneling at the edge, and then control integrate back into the operator's core using like GXGY and S6A. Private LTE, this is not a market that Facebook particularly is focused on, but obviously a lot of the functionality that is available in the platform is available for private LTE. And then expansion networks and the mobile broadband are some of the initiatives that we're working with Whitestack on. These are earlier than fixed wireless and carrier Wi-Fi, but there's going to be production trials around the same in the near future. Yeah, so key tenets of how do we think about a fixed wireless solution is that in a fixed wireless, it doesn't make sense for us to sort of bring back the user plane and the control plane to a central location. So a distributed EPC in many cases makes a lot of sense. It's cloud managed, and so we have APIs that can plug in from the element manager into whatever OSS and BSS and orchestration system there is. The third one is around it being access network agnostic, so 4G and NSA is supported, 5G is on the horizon, or Wi-Fi. In certain cases, if you want to augment capacity at the fixed wireless site with like local Wi-Fi APs, that is also available. Local breakout, this is interesting, especially if you're backhauling traffic at various points in time over unlicensed spectrum. The resilience to jitter is pretty important for both S1C and S1U. The disaggregation and scale. So you don't build out, you don't have to buy a large EPC. You build out site by site. And then 3GPP compliance. So we support S6A, GX, and GY. So you can plug it back into your existing core. Yeah, so this is a high-level data sheet. This is also available on the GitHub page. But the idea here is that we recommend a form factor, and we're working out of the box. It works on Amazon, but if you have a capable private cloud deployment form factor, it should just work fine. At the end of the day, we depend on Kubernetes as our underlay infrastructure, and a lot of these APIs are available for CDRs, data provisioning, and user provisioning.
Thanks a lot, Amar. So tying to the concepts that Amar has explained, we would like to share with you how we are seeing this at Whitestack. All the value that Amar has talked about on how they are designing this open core project. We think that merging its concepts with the NFVO concepts that we bring from the telco world is bringing a lot of benefits to both sides regarding how we design these solutions together to bring a big value to the telco industry. So, but before telling you the details on how we are bringing these open packet cores to Telco NFV, where obviously Open Source MANO has a key role, I would like to connect that with what we did this week at the Hackfest, because it's not that far from that. What we, well, as many of you know, the Hackfest used to be a training, a set of training sessions isolated from each other, where instructors from the community told the story about each module and how it works in independent examples and network services. This time, as a community, we worked together with many companies to build a complete story, and for that we brought the experience that we have already with the Magma open packet core. So we did a lot of things in this scenario, and you will start seeing how this complete packet core that dozens of people were able to launch in minutes is stretchly tied to what the value that we need to bring to the telco industry. So first of all, we managed to virtualize all the components. So all the components are running virtualized in a most efficient way for the particular workload. So containerized or virtualized in KVM, depending on the workload. But not only that, we managed to intelligently place these workloads where it makes sense. And for that, we use the newest placement module of Open Source MANO, and that let us instantiate a distributed packet core built from Magma Access Gateway, first in a data center in France, and after some minutes, another one in a data center in Oregon, US. So this is what Hackfest participants were exposed to just by using OSM placement model. Then we delivered a Evolved Packet Core ready to serve, and by that I'm saying that it was instantiated, and also its day 0 and day 1 operations were embedded in the VNF package. So we converted Magma Access Gateway into a VNF package that OSM will understand and automate. So whenever participants were launching a Magma Access Gateway, it was already ready to receive eNode Bs and subscribers, and already integrated into its element manager, which in the context of Magma is called the Orchestrated, for the Hackfest participants that can remember that. So completely automated, a task that usually takes weeks in the best case of integrating a packet core in an operator. We did it here in minutes. We also embedded automated end-to-end testing, so using open source tools to check that the traffic was flowing through, and with test subscribers, and going up to internet to check that the Magma Access Gateway deployment was okay. Then we were able to orchestrate a complex CNF, the Magma Orchestrator, which is the EPC element manager, is running over Kubernetes, and it's a complex KNF or CNF because it's built out of many components that are ready to handle hundreds or thousands of access gateways in this distributed EPC fashion. So we were able to orchestrate that also in less than a minute. We could have a new orchestrator instance there and ready to manage multiple access gateways, potentially distributed in multiple network slices. We also added PMF orchestration. So all the participants in the Hackfest shared a single router, which was a physical one outside their virtual domains. And they were able to make the network service of the APC aware of this, what we call PNF, making it part of its network service so that it can orchestrate the rules they need to be able to complete all the configurations to make the traffic flow up to the services or internet. We also added network slicing. So everything here is a slice in the concepts of 3GPP, and that I will bring so much value to the 5G use cases. And all participants were able to launch a second slice, and where we kept the orchestrator or the element manager as a shared network network service, so that this second slice just launched the access gateway with its tester and was aware of the local instance of the PNF in the remote data center in Oregon. We also dealt with automating other CNFs, like in this case, it was a web cache implemented through Open Source MANO as well as a KNF, as a CNF, with primitives, with automation, so that participants were able to enable or disable URLs on the fly. We also implemented auto-scaling in policies in the Magma Access Gateway based on metrics that we could gather from Open Source MANO, and using the policy model, taking decisions to add additional instances of the access gateway. So future Hackfests we would add more emulators so that we can load balance this traffic and make a real interesting use case out of it that would make our deployments more flexible and elastic. We also implemented a high performance data plane, so all participants were able to tie these virtual instances to SROB ports, and this brought a higher throughput in the S1 interface. And we also, from Open Source MANO, by using the SDN assist feature, were able to automate the configuration of the underlay automatically. So at the end, all participants were able to just launch the network slice and see traffic flow end to end with all these characteristics in place. So it's really a huge thing, because all or most operators, mobile operators, are looking for this agility in their networks. I for sure want to highlight that this work was a teamwork between all the relevant companies that are driving the Hackfest in the OSM community. So it's not only Whitestack, but many other companies that help build this scenario. So this is already available for everybody as in the context of the open source project. And we are taking at Whitestack this one step further, and that's why last year we partnered with Facebook. We started doing some tests, some POCs with customers to be distributors of this network function in the form of a VNF. So this is the value we're bringing now to the telco industry as Whitestack, as a company. We are distributing the Magma components. We are adding other elements that would let us, that are letting us implement Magma in brownfields. I mean, Of course, all operators or mobile operators have existing cores, and we are introducing the Federation Gateway of Magma also there to be able to start introducing Magma in a phased approach, and this is easy because it's a distributed nature. So all these advantages that we saw in the Hackfest and can be easily mapped to what the real telco needs. Of course, there will be no free switches, so like we were interacting with in the Hackfest. There will be large-scale data center and access networks, but the concepts are the same. And there will be no single router, but large-scale data center and transport networks to orchestrate. And there will be many value-added services from the operators that will need to be automated. And there will be more slices that the operator would need to operate, of course. But the concepts that we reviewed at the Hackfest this week and that we are bringing to the community are that important to the telco industry. As you can see, they map one-to-one to all of these requirements. So I'll leave you now with José Miguel Guzmán. José Miguel.
Thank you, Gianpietro. Hello, everybody. So the basic concept that Gianpietro mentioned about integrating these components, these stacks, is what actually we see as our mission. So the Whitestack is named after the concept of integrating stacks, open stacks. And by using open stacks, we are able to create more complex systems that are leveraging open standards for integration. So the first thing, obviously, that we need to provide is the infrastructure stacks. And that starts with an open infrastructure. So COT servers, white boxes, switches based in Intel and Broadcom, and then our distribution of OpenStack that is called White Cloud, our distribution of Kubernetes that is called White Mist, and our distribution of Open Source MANO that is called WhiteNAV. Once we have that, we go to the functional stacks. The functional stacks are actually the VNFs. Magma is probably the best example because it's a fully functional network service that is carrier grade, is ready for production, and that we are, as Gianpietro mentioned, partnering with Facebook to take it to production. So everything here is possible because we can orchestrate. There is a high-level orchestrator that, as you will imagine, is OSM, and that drive our work here in the community. So WhiteNAV is our distribution of open source MANO. As you may know, we started 2 years ago, more than 2 years ago, to pack OSM in a product and to attend to the plug tests and start interacting with other vendors to test functionality and so on. So for every open source release, we have released a respective WhiteNAV release. So we started with the WhiteNAV Alcobendas, WhiteNAV Barcelona, and later with the release 7, we came with the Casa de Fels. So all cities named after cities where we had OSM meetings. So now that release 8 is coming, we had to find a name for the next WhiteNAV release. It was difficult because finding a city with letter D was not so simple. But at the end, we remembered that in the OSM meeting number 5 in Colorado, we were very close to a city that is what we're using for naming this release. So OSM release 8 is going to be named WhiteNAV Denver, that is in Colorado. And as I said, we're very close to the Cable Labs facilities where we had the OSM 5 meeting, and also is where we did our first exercise of demonstrating an evolved packet core, a multi-vendor evolved packet core in the OpenStack Summit that was in Denver. So Denver is important for us, and it's the code name for this release. What is included in WhiteNAV Denver? So basically, for people that was attending the Hackfest, you're familiar with some of these features. So the VNF repositories is going to be included. a new approach for monitoring VNFs in a more scalable way with Prometheus and SNMP exporters that is going to be also included. SDN support for a couple of vendors, Gianpietro and Arista included. More monitoring. We are going to be integrating alarms and events from the SDN controller so that it will be more operational. Support for layer 2 networking. Support for proxy charms, but in Kubernetes, not only as Linux containers, but in Kubernetes too. High availability for VCA, extremely important. And also, we decided to, and we talked a little bit about that in the previous meeting, we were targeting to include support for Helm charts in WhiteNAV, and it's going to be available. So the deployment method for WhiteNAV Denver is going to be based in Helm charts that make it much easier than our previous deployment approach. And as you know, Helm is a technology that got a lot of support from the industry, not only for applications, but also for VNFs or CNFs that are based on that. So a quick example about how to deploy with a Helm. Obviously, you need to have some infrastructure first, but once you have your cluster and all the infrastructural elements ready, you just install a repo. Then you can see that you will have a release available for that component, that is WhiteNAV. You do a Helm install with some parameters, and creating namespace and so on. And after a few minutes, you are going to have all your Docker images in the cluster orchestrated by Helm, fully operational. So it's a deployment method that we believe that is super simple, but more important than that, is extremely well supported in the industry because there is a huge community of applications using Helm charts. So the next one, and I think that this is just for closing the presentation. So at Whitestack, we are doing efforts to bring all these technologies and take this technology to different environments. So there is a very interesting success story we have with Internet para Todos. That is a project that integrates, as a project between Telefonica and Facebook, where we integrated an Open RAN vendor that is parallel wireless in Latin America. We are in a couple of countries operating with that, serving rural areas where having a virtualized Open RAN was the best approach in terms of cost and agility. The work we're doing with Magma, at this point, focusing on fixed wireless access. As Amar mentioned, that's it's a mature feature in that point in time. But also we are in the more traditional telco cloud environment where we are doing interesting stuff in terms of distributing clouds. There is always this decision about how to manage the control plane, if you are going to have a centralized control plane or you're going to have a distributed control plane. And we have developed an interesting approach based in the edge principles to have large clouds distributing the control plane, but in a very efficient way. And finally, as the end controller integrations, we work with some vendors to automate the data plane and the switching fabric so that we can support all these network services that rely on SR-IOV, providing at the underlay support for that connectivity. So that's a quick summary about WhiteNAV and Whitestock. I don't want to extend it too much because I think that we run out of time, but if there is any questions or comments, please, you're welcome to do it now.
So thank you very much to all three presenters in our last presentation. It's very clear that OSM ecosystem is driving huge steps in network transformation and modernization, and it's just very exciting to see all the progress from all of the different organizations that are participating and contributing to OSM.